see you here. We are starting chapter 10. This is a big chapter all about circles. So today we start with a lot of vocab. And kind of the topic of this first section is called tangents. And it is not the same as the tangent from SOHCAHTOA. So it isn't SOHCAHTOA again. All right, so let's just talk about some circle basics. So a circle is defined as the set of all points that is equidistant from center point. So think about all of these little points here. Equidistant from the center. That's how we form a circle. So when you name a circle, you always name it by its center. All right, so point circle D refers to this circle right here, circle with the center of D, and this is circle K. So it's kind of a new symbol for us. A circle with a little dot in the middle means that we're talking about a circle. The center, gosh, there's not much to define about the center of these circles, at least not that we're going to have to be able to say again. So the center of the circle is always a point. All right, so you could just call it point D or point K. Or you could just say D or K. Okay. So the center is a point. When you have the symbol in front, that means you're talking about the full circle. A chord is a segment joining two points on a circle. So AB is a chord. GH is a chord. And even though this is drawn as a line that goes outside the circle, from N to P is a chord. So if you write it NP with the segment over the top, you're referring to just the chord. A diameter is a chord that contains the center. I always say it's a chord that goes through the center. The only diameter we have on this whole diagram is this one, from A to B or B to A. All right, a radius is a segment whose endpoints are the center and any point on the circle. So the obvious radius is from K out to M. There are two other radii. Plural for radius is radii, radii. Right, so from D out to A, that's also a radius. And from D to B, that's also a radius. And you can name them in the reverse order as well, BD and AD. Okay, so those are kind of familiar terms. Maybe some newer terms would be a secant. So that is a line that intersects the circle at 2 points. Okay, so there is basically only one secant drawn on here. So notice it's a line, not a line segment. So this is a secant. Notice it's a line indicated by arrows, or it goes through the circle. There's an outside part present. So line NP is a secant. NP with the line symbol over the top. We haven't had to differentiate between segments and lines since first semester. Let's see. This does not intersect the circle twice, so it's not a secant. And either does this line right here, right? It has to go into the inside of the circle and then go back out. Hits at 2 points. This is simply a chord. So there's only one set on the whole diagram. A tangent. Now we get to a tangent. Different than, oops, I keep trying to shift my paper, but I need the whole diagram on here. A tangent is different than SOHCAHTOA tangent. So a tangent in this chapter is referred to a line that intersects the circle at exactly 1 point. And it can also be a line segment. So here's an obvious one. Whoop, right? It comes along and intersects the circle at that 1 point right there at J. Okay, so it's the full line. So JL. All right, and then this is also a tangent. I guess I'm jumping around a little bit. It's tangent at point F. They didn't put a dot there, so you can add one in there. And they didn't put a point here, but the fact that they just put a one uppercase letter implies a point. All right, so EF is actually tangent to both circles at the same time, and so that is actually called a common tangent. That's when some line is tangent to two circles. Okay, and point of tangent C is the point where the line is tangent to the circle. So we have a point of tangency at E, F, J. Those are points of tangency. Okay, so this vocabulary ends up being pretty important. You kind of have to know your parts of a circle throughout this entire chapter. We'll kind of practice this for sure in the first half of this chapter. All right, now we do some kind of simple circle things, and then we're going to on to two theorems that one at least, actually both we're going to be using almost for the rest of the chapter. Okay, so notice we are referring to circle A, and we are going to find the radius of circle A. So we go over here. There's an A right here, and we are trying to identify which circle goes with a center of A. Right, so it looks like it's the bigger one, and I'm just going to test it out by counting a radius, right? If I go from A up to the edge here, it's 1, 2, 3, 4. And 1, 2, 3, 4. Yep, and then I'm going to go down 4 to get to that edge, and I can count left 4 and right 4. So the radius of circle R is 4. Diameter of circle B. So here is circle B. Diameter is a measure all the way across, so we're going to have to either go straight across this way or straight up and down. That's the only way we can count actually how long these segments are. So that one looks like it's radius of 2, diameter is 4. Okay, radius of circle B would just be 2. Diameter of circle D. Okay, so here's D. This is the smaller circle. So it looks like if I counted up, it would go 3. Down, it would go 3. Left 3, right 3. Oops, that's a radius of 3. We want diameter. That would be 6. And this is two circles that are tangent to each other, as in they intersect at that one point. Now we're going to practice making a circle. So the circle has a center of -1, -2, and a radius of 5. So the only places that we can't actually count an exact radius is if we go left 5, 1, 2, 3, 4, 5, right? That's from the center out to the edge. Left 5, 1, 2, 3, 4, 5, and up 5. Down 5. We'll do our best to make something that actually looks like a circle. A lot of times they look like little diamonds, but there we go. We can't really test the other points that they have a radius of 5, but we have these exact points right here. All right, more vocab. Coplanar. So the word plane means like a flat surface, a two-dimensional surface. Coplanar circles are circles that lie on the same plane. So that's basically all we're going to deal with in this chapter. So I guess we're just differentiating it right here. Circles that lie on the same plane. Two circles that you draw on your paper would be considered coplanar circles. All right, so we are going to draw two circles that have 2 points of intersection. So it looks something like this, almost links of a chain, right? Tangent circles. So we could either do the kind of figure 8 looking example. They don't have to be the same size either. Or like on the front of the page, we kind of had some circles that looked like this. All right, and concentric circles. Concentric circles, they will have no points of intersection. So those are circles that share a center. Right? So if I just had this circle right here with the center, I'm going to draw another circle that has the same center. So they don't actually ever intersect. Okay, and another phrase, common tangents. Common tangents. So tell how many common tangents the circles have. All right, and we'll draw them. I always draw them first and then I add them as I count. So a tangent would be a line that comes along and touches each circle at one point. So you could kind of see that it would be like this. So the line itself is a tangent, and this line itself is a tangent. So there are two common tangents for this diagram. This diagram has no common tangents, right? This, although it's tangent to the inside circle, it's a secant for the outside circle, the bigger circle, because it actually goes, has these two intersection points, right? If you try tangent to the outside circle, it doesn't even touch the inside. All right, and then these guys are touching right here. One common tangent. .1 and theorem 10.2, both important theorems, but for sure theorem 10.1. This is something that's going to be used throughout the whole chapter. So it says, in a plane, if a line is tangent to a circle, then it is perpendicular to the radius at the point of tangency. The converse is also true. We're going to complete the picture. Okay, lots of vocab. So in a plane, if a line is tangent to a circle, all right, that means a line that comes along and hits the circle at that one point, then it is perpendicular to the radius. So we're going to draw in the radius to that point. And what we know is that they are perpendicular. All right, and that ends up being really important. The converse is also true, although I want to say 99% of the time we just use it in this way. So I think we're only going to kind of talk about this. But why is important? This creates, if I wanted to add another line on there, now I've got a right triangle. I can do some stuff with that. And it's also true if you had a diameter, right? So it does, the theorem says if a radius, but I mean, if you had the full diameter, there's always a radius within that diameter. Okay, and then theorem 10.2 is called the hat theorem. I love the name of this, and it's when I say hat theorem, everyone always remembers what it means. So it says tangent segments from a common external point are congruent. All right, so here's our little diagram. Looks like a little hat, kind of sideways. So BA and BC are tangent to circle O. So that means it comes along, and they didn't extend the little tangent lines, right? They stop right there. But at these points of tangency, right? If you know that that these lines are tangent, this segment and this segment are equal to each other. All right, so we're going to work some examples that apply those two theorems. So the first example is FD tangent to circle E. This is an application of, is this an application of theorem 10.1 or 10.2? Oh my goodness. Okay. Now that I said we're not going to be using 10.1 converse, I think this is an application of 10.1 converse. So let's look at how it goes. Okay, so the converse of theorem 10.1 would be this. Hey, if I could say that this is a right angle, I'm going to put a question mark here because I don't know yet. If that's a right angle, then I would know that FD, in fact, is a tangent by the converse of theorem 10.1. So we're using 10.1 converse. Okay, so I just need to establish if that's a right angle. So we actually go back to some older info, and that is, how do I tell if I have a right angle? I'm going to use the Pythagorean theorem, right? So I know that if a squared plus b squared is equal to c squared, then it is in fact a right triangle. So my a and b would be the legs of this triangle, 8 and 45. All right, and then the c is not readily given to me, right? I need to figure out this entire length right here. So this much is 25. I know this radius is 28, and since it's on a circle, this also has to be 28. So I am going to just add 28 and 25 together, and I get 53 for the whole radius. So I'm just going to test my my angle out with, or my sides out with Pythagorean theorem. So I'll go ahead and do 28 squared, which is 784. 45 squared is 2025. 53 squared is 2809. Okay, let's see, 784 plus 2025 is 2809. All right, so because the two sides are equal, this tells me that I have a right triangle. What a right triangle tells me is that this is in fact a right angle. So I know that EF is perpendicular to FD. And what that tells me by the converse of theorem 10.1 is that FD is tangent to circle E. Whew. Lots of info on that. Okay, now we're using that theorem 10.1 in the what I think is the more standard way that we're going to be using it. So it tells you that S is a point of tangency. All right, so we're using 10.1 says that when a radius meets a tangent at that point, we have a right angle there. That tells us that this is a right triangle. So now we are going to solve for SR. Oh, look at that. SR already is solved for. It's 48. Let's back that up there. Let's just say we're going to solve for the X. Okay, I think that's the intention of the question. Since it is a right triangle, we can use all of our Chapter 7 stuff. It's not really set up for any triangle families. It's not set up for SOHCAHTOA. It truly is just set up for a Pythagorean theorem. Right? A squared plus B squared equals C squared. So A and B are leg and leg. X squared plus 48 squared equals, this is a little tricky, but the C squared is the entire hypotenuse. All right, so it's this piece and this piece together. 36 is only for this outside portion. So X plus 36 squared. Okay. 48 squared. 48 squared is 2304. All right, x plus 3 squared. So it's a binomial. Oh, we have to follow our rules of algebra. We're not allowed to distribute an exponent through a binomial. We have to expand and FOIL. First, outer, inner, last. Okay, so there we go. This actually is kind of a fake quadratic when you think about it. You have x squared on the right, x squared on the left, right? If you tried to subtract them off one of the sides, they end up subtracting off of the other side as well. All right, so we don't have to worry about any factoring and zero product property. Let's see, I have limited space here, so I'm going to combine some things. 36x plus 36x, they make a 72x, and it looks like all my x's are on the right. So I am going to minus this extra number from the right. And I'm going to do 2304 minus 1296. And I get 1008. All right, so 14 equals x. All right, man, I need to get some numbers on these examples, but this right here, right, we are told that AD and BD are tangent to the circle, and I mean, it just looks like a hat, sideways, albeit, but a hat. We are applying the hat theorem. So when two lines are tangent to a circle, two segments, what I'm going to say by theorem 10.2, the hat theorem, is that these two pieces are congruent. All right, so theorem 10.2, maybe better calling it the hat theorem. I know that 6x minus 8 has to equal 25. So I am going to set that up in order to solve for x. All right, let's see. Just divide both by 3, right? 11 halves, it's okay to leave it improper. Okay, and another hat theorem. All right, so it doesn't give you the words that the segments are tangent like it did on this first example here, but it tells you with the picture. So those right angles end up being important because it tells you, right, by theorem 10.1 that if a radius and a segment are perpendicular, then this segment is tangent to the circle. So that's a tangent, that's a tangent. I'm going to use the hat theorem. Again, these two pieces are equal. So I can say x squared plus 7 equals x minus 1 squared. X minus 1 squared is x minus 1 times x minus 1. Then I'm going to do the distributive property, or FOIL if you like it that way. X squared minus 1x minus 1x plus 1. Another fake quadratic. So if I subtract the x squared from the left, it also subtracts from the right. So we don't have any x squareds left at all. All right, so bring down the equal sign. I'm going to combine steps again. This plus 1 has to go off the side that the x term is on, right? All I've got here is a negative 2x minus 1 minus 1. Okay, this part on my printer, I thought it was, I'll have to check my notes, but that should be on the next page. This is the end of this video, and the common tangent procedure will be